Okay, so getting back to where we were in lecture now. I should ask if there were any questions that came up from last time before we go on. Yeah.
When you discuss the massless scalar field action,
Yeah.
You mentioned that it's conformally invariant in 2D.
Yes.
Why is that of any interest to us?
For this, as far as this course is concerned, it's only because it's it's part of the law of relativity in curved space and scalar field theories. But it's of great interest to many people who love to study conformal field theories in 2 dimensions, and that's because it goes way back, but I suppose these days the strongest motivation for people to do that is string theory, where the equation of the string is defined by some sort of scalar field or many scalar fields living in 2 dimensions, and they take care to adjust those to be conformally invariant. To preserve the conformal invariance at a quantum level. So it's one of the crucial inputs to string theory. But it's also just an interesting, another reason why, 2D often comes up one way or another by dimensional reduction. Like if you're considering a 4-dimensional problem that has both, say, time translation invariance and rotational invariance, say axial invariance, then you're really reduced to a 2-dimensional problem. The only coordinates that remain relevant are r and let's see what I want to. Let's say it has. Yeah, the only coordinates that remain relevant in that case would be r and theta. The polar angles, like for a curved black hole or something like, or a rotating star. So once you're dealing with 2-dimensional problems, you often see things like the scalar wave equation coming up. And it's useful in analyzing it, in remembering that it's conformally invariant. So it's kind of a useful just fact to file away. But the greatest interest, I think, attaches to conformal field theories, which are by many people regarded as the most interesting of all field theories, which really means the ones that we can make the most progress on understanding. It's this old, searching for your keys under the lamppost effect. But also in string theory, they're specifically of importance. Okay, so I guess we just finished talking about the temperature redshift. What we found, I guess, what we started with was the fact that when you have a killing vector, see that this combination, which if it's a time-like killing vector, you could call minus E, the energy with respect to infinity, as defined by this killing vector, where the killing vector is assumed to be normalized so that, when I say with respect to infinity, we assume that it's normalized so that it becomes just the unit time-like vector in some direction, some frame, at infinity. So this was conserved, and this is conserved. We saw that it was conserved for any geodesic motion, any freely falling particle, and we derived from it the result that for a system in thermal equilibrium, in a static or in a stationary gravitational field, that the relation between the locally measured temperature and the temperature measured at infinity, which is, I won't review everything, is just given by the norm of the killing vector c. This is this redshift factor that we saw before. If we remember that the norm of the killing vector is equal to just the square root with minus sign of G00. Okay. So the only other thing I wanted to say was to comment, so sort of where the last lecture got cut off, I wanted to comment that this is really the same, or it's intimately connected with the redshift that we found earlier when we talked about photons propagating in the gravitational field. In that case, I think we talked about a weak gravitational field. Here, there's no necessary requirement that it be weak, but what we are requiring is, of course, that Xi be a killing vector. And why is that? Well, the point is that what does this perceive? I mean, here we talked about T local. Now let's just think of some photon, for example, propagating in the gravitational field, and ask what a local observer who is aligned with the killing vector Xi, so someone who is at rest with respect to that killing vector. So we're talking, if you like, about a coordinate system in which the metric components are independent of time, and in that coordinate system, we're talking about an observer who's at rest. What energy will they, or what frequency, if you like, will they attribute to this photon? And the answer, of course, that if the observer is defined by the world line A, a world line whose tangent, so the world line of the observer, say, is gamma, its tangent is the normalized vector u, then they see, that means in their reference frame, that's the zeroth basis vector. And so they see the component of the form momentum of the photon corresponding to this basis vector as what they call the energy. That means, and that of course means that their local energy is just equal to, with always this minus sign, is equal to u dot p, p being form momentum of the photon. And that's equal, but that's obviously proportional to this, but not equal, because what is their u? Their u has to be a normalized vector, and so it can't be Xa itself, it has to be Xa divided by the norm of Xi. And so that really means it's minus Xi dot p divided by the norm of Xi, right? And this is E local, and this was equal to E infinity divided by Xi. So the conclusion is that E local, that E infinity, if you like, E infinity is equal to E local times the norm of the killing vector Xi at the point where you're measuring the local energy. So in other words, energy, in general, this killing vector gets shorter as you approach, say, a massive object. That's this redshift, or the slowing of clocks. And so what it means is that the energy measured there of this photon, from the point of view of infinity, will seem less than it seems to be locally. And that's the same thing, of course. At least that's closely connected. For self-consistency, it must be equivalent to the fact that when the photon propagates out to infinity, it loses energy, and it shows up with this energy, the infinity. That was that comment. So along the way, notice that we've defined the gravitational redshift for photons more generally than we have, in fact, for any particles, more generally than just in the weak gravitational field limit that we thought about before. This equation is then true, because this equation is true in general as long as you have a killing vector. This is also true. So it implies in the neighborhood of a very massive, a very strongly gravitating object like a neutron star or something also. Okay. So before we get on to applying some of this to the Schwarzschild metric and the orbits of particles in the Schwarzschild metric. Let's, I want to go back and rederive the main result in a somewhat different way. We did something that was very tricky or clever or whatever you like to call it, or maybe it's really just very straightforward, which was, however, to start from an action principle. So once you start from an action principle, it's very straightforward and very simple. But you should also be able just to start from the equations of motion and derive the same result. Once you know the equations of motion for geodesic motion, that has to contain everything. So can we derive the conservation law that way? And the answer, of course, is yes. So let's see how that goes. This will now use, crucially, some of the properties of the covariant derivative that we established. I'll remind you that, interestingly enough, when you start from the action, you don't actually, I mean, at least in the cases we looked at, we didn't ever need to introduce the covariant derivative because it wasn't there in the action. The metric was there, but not the covariant derivative as such. But here we will use it. So remember that we had this general formula that the form momentum is given by the rate of, by this tangent vector to the curve, the geodesic curve, parameterized by this lambda, which is an affine parameter. And then when lambda is an affine parameter, we got the equations of motion to be this, where this represents differentiation with comparison using using parallel transport. So that was the equation of motion, which therefore means, if we write it out more fully, it means, what is this P? It means d by d lambda of dxa d lambda equals 0. Remember, this just means the tangent vector to the curve, but this capital D is reminding us that we have to use parallel transport to do the comparison. And if we write out in terms of the covariant derivative operator as is convenient and as we've been doing, then this implies that, let's first do this. So this d by d lambda, remember, is dx. This d by d lambda here can always be read as dxb d lambda times grad b, right? So if we can put those together, then you find that, and then furthermore, of course, dx to d lambda is p. So therefore, this equation reads, if we write it like this, then it reads that pb grad b pa equals 0. So this is general for any geodesic. But now, now let's take this equation, and we're aiming, of course, to get a conservation law. Let's take this equation of the form that we know. Let's take this, so what can we do? We can take this equation and dot it into xi. So then it implies that xi, so we just have pb grad b pa times xa equals 0. Which if we rearrange this, so that says pb times grad b times pa ca. I'm throwing the derivative onto the xi, right? Minus pa grad b ca equals 0. And therefore, well, this is what we're interested in. So we get this is just p times the gradient of this scalar here, p dot xi. And so this is just dc, this is just d by d lambda of PA CA, and this is therefore equal to this other thing, which is P, let's write it like this, GAB PA grad B C. What have I done? Yeah, grad B CA. Right? Now this, I needed something else. I need to,
There should be a
a PB here somewhere, yeah, PB. Now this is symmetric, obviously in A and B, therefore I can symmetrize but this you recognize as the Lie derivative, so of the metric. So it's 1/2 the Lie derivative of the metric times PA PB. Therefore, so we learned two things. So therefore, if it isn't killing vector, so that leak C of GAB equals 0, then it implies that this derivative along the world line of P dot C is 0. So in other words, it implies that it's conserved. And that's the main result. So let's see. So this was the main first result, that the derivative, that d by d lambda, I'll just write it again, so I can have it all in one place. So you directly see that if it's a killing vector, this is conserved, and if there's not a killing vector, then the amount of non-conservation is related directly to the Lie derivative, the failure of C to be a killing vector, the Lie derivative of G. And this lets us see one other thing, which we could have but didn't derive from the action principle also, which is the special case that is relevant to light. So suppose we see that if the Lie derivative of G is 0, then of course we get 0 on the left-hand side. But in the special case where we're dealing with light, so basically that is we're dealing with zero mass particle, then this actually becomes, can vanish even when the Lie derivative of G is not 0. It suffices that this be what's called a conformal killing vector. So here comes conformal again. So if the Lie derivative of the metric is not 0 but is proportional to the metric, then it's called a conformal killing vector. Some proportionality factor, which I've just named as 2 omega. Then we get, in that case, what will happen is that this will become then d by d lambda d dot c will equal 1/2. But then you see this in the massless case, of course, p dot p is 0. It's light-like. The tangent vector is light-like. And so we get PA, we get 2 omega PA PB GAB, and this is 0. Right? Well, that equals 0. So if it's a conformal killing, this is actually can be quite useful in analyzing things in cosmology, in these simple Friedman, Robertson, Walker type of cosmoses, which are just like the one we studied, or simple other analogs of that with flat or spatially negatively curved metric. In that case, time evolution or time translation is actually a conformal killing vector. And that's related to the fact, well, just take, yeah, for now, just take it as a fact. That's a conformal killing vector. And so this lets you analyze something about the propagation of particles in fields, in this case, particles in a Friedman, Robertson Walker background. Oh, one that, is that what so yeah, any questions on this? Yeah.
Is there an easy way to realize that a metric has conformal killing vector just by looking at its component?
No, I don't think so. Well, that's so. Well, yes. I mean, easy, no, but not necessarily easy. But if you can show that the metric is conformally flat, for example, then it must have a conformal killing vector, because if it's flat, then of course it has a killing vector, because we know that it's like Minkowski space, and it has many killing vectors, many symmetries of Minkowski space. If it's conformally flat, then I mean, how can we say it? This is another one of these things that are obvious that I keep claiming. You should learn why this, I mean, you should convince yourself that this is obvious. The conformal killing vector only cares about the conformal metric. I mean, whether there's a conformal killing vector or conformal symmetry only cares about the conformal metric. In other words, it's insensitive to making conformal transformations on the metric. You know, what we call the conformal transformation on the metric is something like this, where this omega is allowed to depend on position. That's a conformal transformation. But it doesn't change what's called the conformal metric, the thing which is independent. You know, if you like, it's an equivalence class of metrics, or you can identify it with the metric divided by its determinant to the 1 over d. But anyway, it's basically the things that determines where the light cones sit. That's the conformal metric. So whether there is a conformal killing vector only really depends on the conformal metric. So if the spacetime is conformally flat, meaning that it takes the form of a flat metric times some local factor. So if this were to go to A to AB, let's say, then the spacetime would be conformally flat, and then it would follow that since flat spacetime has all these killing vectors, which are and even more conformal killing vectors, a few more, that all of those will still be killing vectors of this metric. So only in that case, maybe, if you can recognize by looking at it that a simple conformal factor, or Weyl transformation, as it's sometimes called, can make it flat, or make it anything that has a killing vector, or make it anything that has a conformal killing vector, then it'll also have a conformal killing vector. That's actually why the FRW cosmoses are like that, because they're conformally flat. But you don't even need to know that. Like in the spherical case that we looked at, by a conformal transformation, you can make it a sphere across the line. And a sphere across the line has a real killing vector, a time-like translation killing vector. So therefore, the actual expanding or contracting cosmos must also have at least a conformal killing vector corresponding to that, and does. Yeah.
Is there a reason why you chose two?
Two, yeah, because I was thinking of this. I was thinking the sort of infinitesimal version of this. Normally you tend to put omega squared because I don't know why, really. I guess, so omega will be like a length, basically, and not a length squared. Also, it'll guarantee it to be positive, which is important, so that the signature is preserved. But it's just because of that. Yeah.
I meant the lowercase omega.
This one, yeah. So if we think of this, see, this is a conformal transformation. A conformal killing vector is an infinitesimal type of infinitesimal conformal transformation. So if we were to say that omega was equal to 1 plus little omega, where we think of a little omega as a very small number, then omega squared would be 1 plus 2 omega. That's where the 2 came from. So it's natural to. So, because one final comment. So that's all I wanted to say about deriving conservation laws, at least in the particle case. We didn't go and do the field case yet. But things are rather similar there. But I wanted to make one general remark about what happens when you don't have killing vectors and what's the status. This is a whole topic which maybe we'll have time or maybe we won't explore later. But what becomes of conservation laws in general in gravity? And there's two things to worry about when you try to think, well, what would I mean by conservation of form momentum? I mean, you remember that in Minkowski space, you can always define this form momentum vector, and also angular momentum vectors, which I won't bother with here. You can define angular momentum tensors, also. But you can define this form momentum, and we know that it's conserved by any process. At least we believe that if you take into account all contributions to this, then you'll find that it doesn't change with time in flat space, basically because we believe that the fundamental theory can be described by an action principle, and then we can apply a form of Noether's theorem to get this result. And that whatever other reasons that may be for the belief, we believe that this is conserved. But what can become of that fact in the context of general relativity? The first thing you might worry is, well, this is strange because this is a 4 vector. Now, and I got it by adding up all the local contributions all over space at a moment of time. But what does it mean if I go into curved space? How can I add these up? These are 4 vectors at different places, and they can't be compared. They just live in different tangent spaces. The only way we know to compare them is by parallel transport. So you could transport them all back to one place, like your center of the rotating. We could do that, but then along which path should we translate them? Right? We have no symmetry to go on in the general situation. Every path that we translate them on will transport them on, will bring us back to a different value. So there's not even a good candidate for what this should be. If there's a killing vector, then we've seen that we overcome this by not working with this, but by working with a scalar, namely with CAP, the local sort of PA. That's a scalar, so it makes sense to add them up. And so in that case, that particular worry goes away, and in fact, you do get a conservation law. But suppose there are no killing vectors. What should you do? So the answer is, in general, as far as I know, you just give up. Right? I mean, there's no conservation of energy and momentum and so on are just lost, or you might say transcended, if you like, a fancier word in general relativity. But on the other hand, there are plenty of situations where you believe there should be conservation of energy. Like if you drop a brick into a black hole, you expect the mass of the black hole to go up by the amount of energy in the brick. And that's a form of conservation. If we can't talk about it at all, and there's no killing vector in that situation, right? I mean, the brick is moving around. It's not spherically symmetric, blah, 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 blah. Black hole at best is symmetric after it settles back down, after the brick has been dropped in. So how do we do it? So the answer is, if there's so this goes back to what we discussed early on. If there's a background structure which is invariant, then you can apply the symmetry to the subsystem and not the background. I won't review the whole discussion that we went through. And you can hope to get a conserved quantity, and that's actually what happens. So in the case of what's called asymptotically flat, and there are other cases like asymptotically anti-de Sitter is a very popular one these days. But anyway, the realistic one for astrophysics in the world that we live in is asymptotically flat. So it's that's an isolated system. It's isolated because it's surrounded by a region that's sort of empty. Nothing's happening, just a flat region. When it's asymptotically flat, then you can actually talk about translating the subsystem with respect to this background flat metric that's near infinity. And that does lead, again, to a conservation law. And the way you overcome this is subtle. The fact that you have to have a 4-vector or even an antisymmetric tensor for angular momentum, it's quite subtle. You don't do it by taking the little individual contributions. There is no well-defined localizable energy density when you include gravity in special relativity. In general relativity, unlike special relativity. But nevertheless, there is a way of defining a total energy or total momentum which has to do with so you have like this isolated system, and then there's infinity out here. And if you do some sort of translation on this isolated subsystem, it gives you a notion of total energy, and that total energy and momentum, form momentum, this thing actually lives at infinity. So since it lives at infinity and infinity is flat, it's now okay. I can translate it from any place in infinity, anywhere else that's in the asymptotic region, and I get a self-consistent notion. So there's something, so to speak, as the flat space at infinity. You might regard it as something like the tangent space at infinity, which is defined in this situation, and the form momentum lives there. Yeah.
What are we taking as asymptotically flat? The background?
No, so the actual space-time should be asymptotically flat, and then the background is the sort of fictitious, not fictitious, but it's kind of like a fictitious extension of the flat metric at infinity into the interior. So physically, it represents the flat environment, or the environment which is so far away that it's basically decoupled from whatever is going on locally. Yeah, so that's right. So we're taking that flat metric, which is fictitious in a sense, but which becomes the real metric as you go to infinity. And we're treating that as the background. So if you like, I guess a better way of saying it would be that the environment is the background. We're only applying our partial isometry to the subsystem. Another question?
Yes, I was just going to ask. So essentially, we're still doing system transformations to get and symmetries to get conserved quantities.
Exactly.
This time we're applying it over the entire black hole, for example.
Entire black hole, yeah, yes,
Black hole
and the brick and whatever else is interacting with the black hole. Yeah, that's right. That's exactly right. Yeah.
You are saying the form momentum is defined as infinity.
In the case of gravity, I'm saying that in general, yeah, form momentum can't even be defined, but when you have an asymptotically flat space-time, then you can define the form momentum at infinity.
So, let's say someone is at infinity, and they can define the form momentum of that smooth place because they see it as flat.
No, it's just that it's like they're using infinity as the reference. So it's not that it's all so far away it looks flat or something like that. They know that it's very highly curved in the interior, but they use this technique to define a form momentum which corresponds to. Let's think of a wave function, for example. So for form momentum is a sort of sinusoidal dependence of the phase. You know what I mean? It's like an e to the ikx dependence. It's not that they see that thing in some sense as flat, but they see it as point-like. They see it as just some isolated thing, which could be translated, and if it translated a certain amount, it would pick up a certain phase. So they're seeing it as a sort of, I think point-like would be a good word for it. So the whole thing is like the whole black hole, all the junk, whatever, the stars, and that in this isolated region, they're seeing it as if it was just one particle, and then they're attributing a form momentum to that. But it's not so important that they see it. I mean, extended objects also have form momentum. It's not really that they're claiming it as a point. It's that they're just treating it as an isolated object, which can be regarded as a single object living in the flat space-time that they inhabit. Yeah.
You said in general we can't define the form momentum. You mean the total form momentum?
Right.
Okay.
Well, but also you can't define a local form momentum. So in the case, in the asymptotic, I mean, this is crucial. So in the asymptotically flat case, I'm claiming you can define a global form momentum. And then you could ask, could I define a local form momentum such that when I added up together all the local form momentum, I would get the global form momentum? Okay. And the answer is both no and yes, right? The answer is no, there's no unique definition, but yes, there's an infinite number of inequivalent definitions that give different values to the local form momentum. But when you add them all up, you get the same value for the total form momentum. So that would have been a more precise statement. There's no invariant notion of a local form momentum. And the reason that it's not there, you can see it actually from the equivalence principle, which is, remember at least you can see intuitively why this is what you would expect from the equivalence principle. Remember that when we were discussing that, and when we were discussing what we were just doing, defining the covariant derivative, we found that there's always some local reference frame in which the gradient of the metric is equal to, gradient of the components of the metric tensor is 0. But we also saw that these gradients, they precisely enter into the Christoffel symbol. They're 0 if and only if the Christoffel symbol is 0. That's basically how we define the covariant derivative. And the Christoffel symbol is the thing that you identify naively with a gravitational field. You have to go back to when we talked about the weak gravitational field and the motion of a particle in the weak gravitational field. Remember, this gave a velocity-dependent force. It's just a geodesic equation. So these are like components of the gravitational field. But here now, I mean, not the gravitational field in the sense of we often use it to mean the metric itself, but in the sense that it corresponds, it's the force field, it's the thing that determines the force on a particle in the Newtonian approximation. So let's just think in a Newtonian situation where we're near to flat space, a weak field situation. We know there is conservation of energy. We know how it works, right? I mean, when the planet comes close to the sun, it speeds up, and when it gets farther from the sun, it slows down. That's conservation of energy in the Newtonian sense. That has to be the same. It has to be, if we have a conservation of energy in the four-dimensional relativistic sense, that has to be, in that limit, has to coincide with the usual Newtonian conservation of energy. We saw that sort of when we discussed the weak field. But where is the energy? How is there energy? What's happening is you're trading kinetic energy for potential energy. But potential energy is, from a field point of view, the energy in the gravitational field. Just like when you're doing electromagnetism, the potential energy of two charges is really the energy in the Coulomb field, combined Coulomb field of the two charges. So we have to, if we want conservation of energy to come out, to make any sense at all, we have to attribute an energy density to the gravitational field. And it would have to be negative because the gravitational field is attractive. So, I mean, up to an overall additive constant. So what? So therefore, if we can't localize the gravitational field, we won't be able to localize the energy associated with it. But what this shows us, the existence of the locally inertial reference frames, or I think I was calling them momentarily inertial reference frames, what that shows us is we can't localize the gravitational field. We can always, in the neighborhood of some point, we can make the gravitational field vanish. Or at some point, we can make the gravitational field vanish. So there's no expression we could write down, no invariant expression that would represent the energy density or the form momentum of that field. The only case is when you have this test particle moving in the background field, somehow you get away with it, and that's what we've just done. Right? So if you work out the energy of the killing vector from this definition, in a weak gravitational field setting, you'll see that it has two terms. One of them looks like the kinetic energy, and one of them looks like what you would have called the potential energy of that particle in the gravitational field. But as soon as you try and attribute the energy to the gravitational field itself, you get into trouble. So basically, one could choose any coordinate system one likes. Having chosen that coordinate system, you can define something that you would call a local energy density that will include the contribution from the gravitational field. And if you integrate it up, it will give you the total form momentum. But it's completely dependent on coordinate system, and therefore it's a very limited use. I mean, to try to localize the energy density is a very limited use. It doesn't stop people from trying. There's a whole, ongoing enterprise called looking for quasi-local mass. Well, maybe we can't absolutely localize it, but maybe we can quasi-localize, in certain situations, although we can't talk about the energy density at this point, or the form momentum density at this, we can talk about maybe the amount of form momentum contained in this region. But then and that would be very useful if you could, like in exchanging energy with a black hole and so on. But then you immediately have this question, where is this energy living? And well, there's a long story that goes with it. Okay, so let's make a start anyway. I'll go a couple of minutes later since we got a very late start. Let's make a start, unless there are more questions on this conservation laws, killing vectors and stuff. Okay, so then let's make a start on the Schwarzschild metric. So this is another topic, but it relies heavily on what we've just done. Particle motion, Schwarzschild metric. The reason it relies heavily is that the Schwarzschild metric is so symmetrical. It has a lot of killing vectors and a lot of conservation laws, so many that it makes it quite easy to almost solve the equations of motion in closed form. So some references for this are Wald section 6.3 and Schutz section 11.1. So we're not going. So we're doing everything. We're doing everything sort of starting at the end and going. So we started with cosmology, not knowing, not having derived basically anything, but I just wrote down the action principle for you. Now I'm going to write down the metric, the Schwarzschild. Now we're going to derive some things, motion of the particles in the Schwarzschild metric, but not the Schwarzschild metric itself. So I'm just going to write that down for you. Then the reason is that to derive that, we'd have to first derive the Einstein equations, and that would be a whole bunch more differential geometry. We'd have to define the Riemann tensor, Riemann curvature, blah, 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 blah. Volume element we've already done. We'd have to go through the variation of the Einstein-Hilbert action and so on. So put that off. So we'll do that maybe next after this. And then we'll be able to actually derive the Schwarzschild metric. But let's just suppose we're given it. Most people will have seen it before anyway. I'll write it in this form. So it's of course, it's the metric of, it turns out by something called Birkhoff's theorem. It's the metric in 4 dimensions anyway. It's the metric of an arbitrary spherically symmetric source. It's of course, it's a vacuum metric. That is, it's the metric of the solution of the pure gravitational field equations. It's not correct when matter is present, but as long as the matter is not present where you are, and the matter is spherically symmetric, then you have a portion of the Schwarzschild metric. It doesn't even have to be stationary. I mean, you could have like a pulsating sphere of like a star that was oscillating or something. As long as it's not rotating and it still retains its spherical symmetry, outside you won't see the oscillations. You'll just see, in the gravitational field anyway, you'll just see this Schwarzschild metric. So it's so basically it just comes from spherical symmetry, which means SO3 symmetry, rotational symmetry. But the Schwarzschild metric itself has an extra symmetry, which is also stationarity. It's actually time independent. That is, it also has not only SO3 symmetry, which infinitesimally means 3 infinitesimal rotations corresponding to the 3 components of angular momentum, but it also has a time translation symmetry. Okay, so this actually implies also the T translation, time translation. And then there's, of course, some reflection symmetries. But as far as the continuous, I should have commented that when we talked about Noether's theorem. It only derives conservation laws not from every symmetry, but just from every continuous symmetry. What in mathematics would be a Lie group. Right? If the symmetry has an infinitesimal version, then you'll get a conservation law, because the Killing vector is, of course, just an infinitesimal symmetry. There are other symmetries like parity, reflection symmetry, which lack infinitesimal versions. And so they don't have, Noether's theorem doesn't apply to them at this classical level. Although, interestingly enough, it does apply at the quantum situation. You do get a conservation law. So anyway, since we're classical here, we won't get extra symmetries from the reflections, but we do have spherical and time invariance symmetries. So now I'll just write the line element in the following form. dr squared over h squared plus r squared omega squared. Where this, because of all these symmetries that I mentioned, nothing will depend, this h will not depend on either time or any of the angular coordinates, but only on the radius. And it takes the form 1 minus r naught over r. That's really all you need to know for the Schwarzschild metric, where r naught is 2gm. In case you like to put back c squared, then it's 2gm over c squared, which Gesundheit. If we're not going to be writing g explicitly, then I'll write it usually as m over 4 pi. That might look peculiar to you. You might be used to seeing 2m, but that's because I've set 8 pi g. The sort of cosmologist units, 8 pi g equals 1, and not g equals 1. So c equals 1. So in those units, this r naught is m over 4 pi. So not to make it more confusing than it needs to be, I'll just keep it as r naught. And then you can, if you like, g equals 1, you can call it 2m. Or if you like 8 pi g equals 1, you can call it m over 4 pi. So that's the Schwarzschild metric. So what killing vectors do we have? What symmetries do we have? We have, so you can see it depends only on R. Therefore, it means that we have this full symmetry, SO3. In fact, we have also reflections, why not, cross R, which is the time translation. And so we can look, and then we even have time inversion symmetry. So there's a Z2. So I think that might cover everything. Have I left? Just for completeness, I think that's all the symmetries there are. But as I was saying before, we only really care about the infinitesimal symmetries, the killing vectors. They're the only ones that will help us to solve the geodesic equations. So what are they? So this is the time translation killing vector, which I'll call XA, and that in our coordinate system here that we've used in writing this line element, that's the 0 or time basis vector. Right? So this is just saying that nothing depends on time. None of the metric components depend on time in this basis. Furthermore, there's the rotational killing vectors. I'll call these zeta. So for example, there's 3 linearly independent. If you remember the fact that the rotation group has 3 generators, which everyone knows in the form that there are 3 components of angular momentum. I mean, a rotation is generated by a vector and by a vector. So it's a direction and angle. So there's two parameters define the direction, and then one defines the angle. So the rotation group is a 3-dimensional Lie group, and therefore it'll have 3 linearly independent killing vectors. Every other killing vector will just be some linear combination of those 3. And that's, so one of them sort of rotates in the 1-2 plane. It's the rotation about the z-axis. And the other 2 are made analogously. So how would we write this? So I'm trying to write the killing vector, but I'm making use of these coordinate functions that we have. So of course, I'm using the usual thing that x is defined r cosine theta. Actually, I noticed cosine phi, and y is r. Oops, no, this is sine theta. Sorry, r sine theta, sine phi. That's, for me, that's the convention I've always seen. But I noticed in the problems that other people must have seen other conventions. Some of these sines changed to cosines, and these 2 switched around, and phi and theta switched around. Anyway, that's the one that I'm used to. So that's the x that I'm in here. So what is the rotational killing vector around the z-axis? It has to be the infinitesimal displacement suitably normalized that comes from rotating by an infinitesimal amount around the z-axis. So if you think about what it is, it's this vector. Right. If you like, it's something like the wedge product of the radius vector with the, what am I trying to say? With some other orthogonal. Well, that won't shed much light on it. So let's just leave it like this. So when you're at a point on the x-axis, so that y equals 0, then this just tells you that you move off. Yeah. Or, let's see. Do I need to say this, or is it all obvious? Yes, which? I should say it, okay. So if this is x and this is y, so z is coming out, let's say. So what does this vector field do? Of course, it's purely space-like. It's not supposed to go in the time direction, so there's no et here. And it's not supposed to move you in the z direction, so there's no ez here. But it is supposed to move you around in the xy plane. So when I'm off in the x-axis somewhere at a location x with y equals 0, then this term, this y is 0, so this term vanishes. So I have x times ey. Ey is the basis vector pointing in the y direction. So this is just telling me that the farther out I go, the bigger the killing vector. And as I go in the negative direction, of course, it becomes big. So this is what happens to the x-axis under an infinitesimal rotation, or under it. In this case, think of this infinitesimal. It goes over to that. The x-axis goes to that. If you think what happens to the y-axis, then you're in a situation where x equals 0, and you get another term. And if you think it through in the same way, you'll see that it's a bunch of vectors like this, as the two axes are rotating around. So that defines that's a formula that gives you the killing vector for rotations in the 1-2 plane. And then similarly, there's a killing vector for rotations in the 2-3 plane, which is strictly analogous, and another killing vector for rotations in the 3-1 plane, which is also strictly analogous. Oh, and I forgot to say, I think it's completely obvious from the other things, z itself is r, I haven't used it yet, but I would in these formulas, is r cosine theta. Okay, so these gives us several conservation laws. You might think a huge number of conservation laws, because it's giving us 1, 2, 3, 4 conservation laws. However, not all of them are all that useful. They're all useful, but not all of them are going to help us not all of them are going to help us in solving the equations of motion, other than to make very simple observations. So the first thing to notice is that I said this here, but I don't understand it. Maybe someone. So I said, by reflection symmetry, every orbit lies in some plane through the origin. So I'm thinking of the spatial orbit now. Here's the spatial. Here's the black hole or the star, whatever is generating the Schwarzschild metric. Now there's a symmetry that x, y, z goes to minus x, minus y, minus z. So how does it follow? Therefore, it's supposed to follow that it lies in a plane. I guess the statement is, I see how, yeah?
Got no reason to go one way or the other.
Yeah, I think that's it, yeah. That's the explanation, right? Thanks. So if you imagine that you're the star, let's say, and then if I happen to start moving in this direction, then exactly by that, there's a reflection symmetry that tells me, so I'm moving in this, I'm not moving in the z direction. If I had a reason to move up into the z direction, then I'd have an equally good reason to move in the minus z direction. Therefore, since everything is deterministic, I won't do either. So I'll just stay in the xy plane. So if I start in the xy plane, I'll remain in the xy plane. So this implies we can assume, or what's called, never mind, without loss of generality, as people say, we just can say that z equals 0. So that is an orbit in a plane. Now, unfortunately, two of these very useful conservation laws become useless because now there's no angular momentum in either the 2-3 or the 3-1 sense. These two, when we dot these two killing vectors into, is that right? Yeah. It's not quite true. Why is it? But they do become. They're not giving us any useful. What's going on? They're not giving us any useful information. Yeah, somehow. I can't quite see it now, but if you think it through, you'll see that you learn nothing more from these two second ones. But this one we'll learn still quite a lot. So we still retain one. Basically, we're saying it's now moving in a plane. And of course, conservation of angular momentum in this plane, or conservation of angular momentum about the z-axis, gives us Kepler's second law, or whatever that law is, that tells you how rapidly the planet moves along in its orbit at different points. So that one is useful, and then of course the other one gives us conservation of energy. So I did write the J. Yes, I see. I guess the point is not that, the point is that these other two killing vectors will always give us zero. They'll always give the answer zero, because if you think of if this is the x-axis, let's say, and you think of this planet or this photon at the moment that it's moving orthogonal to the x-axis, and then if we take the angular momentum about the x-axis, we'll get zero. Right? And the same thing about the angular momentum about the y-axis. So we'll get a conservation law, but it'll be kind of a boring conservation law. It'll just tell us 0 equals 0. Anyway, so yeah, in fact, you could turn it around and use that conservation law to prove that it stays in the plane, but we already got that from symmetry more simply. So let's make a catalog of what conservation laws we have and compare it to the equations of motion. So now what remains is the time-like killing vector, this rotational killing vector, which could also be called, if you were to use not Cartesian, but angular coordinates like we actually have, if you think about it, this is the phi basis vector of that coordinate system. And corresponding to them are then two conserved quantities, which, in order to make it be positive at infinity, we always put this minus sign. I mean, to normalize, to choose the sign of the energy in the way it's usually done, we, as always, have a minus sign. So Ca dot Pa is the energy, which in this coordinate system, going back to what Ca was, wherever it is there, this is just Pa times Ea0, which by definition is P0 in these coordinates. So the zeroth component of, or PT, I think I called it, same thing. So the energy is minus this, minus this, minus this, minus this. And the other one is the angular momentum, which is then zeta A. Well, I'll drop the 1 too, since we're not considering the other angular killing vectors. That's zeta A Pa, which, by the same token, I haven't put a minus sign here now, so it's just P phi. So those two components of the form momentum are conserved. That's two conservation laws. And then there's one other thing that will help us, which I'll say in a second. Yeah.
Sorry, I was just going to ask, shouldn't zeta have some dependence on the distance from the z-axis?
Oh, yes, it does. You see it here.
Yes, but in the expression zeta 1, 2 equals E phi, that is dependent.
Oh, I see what you mean. So it depends what you think E phi means. But you might think it means the unit vector tangential to the circles. That's not what it means. This means the basis vector of the t r theta phi coordinate chart. If you go back and you see how we define the basis vector corresponding to a coordinate chart, then you'll see that there's no r there. Because it means, in other words, when you go, what this killing vector generates is motion by a constant amount in phi. And that's what a rotation is. It's motion by a constant amount in phi. You have in mind some flat metric on the what you're actually thinking about is an orthonormal basis. But this is not an orthonormal basis. This is a coordinate basis. And that orthonormal would have been with respect to some flat metric, probably what you were thinking about, which is also not what we have. Right?
So J isn't dependent on the radius either? Or at least not in terms of P.
Not in terms, well, I'm not sure what that means other than to say that it's just dotting this into E A phi. Okay, let me just state, since it is getting a bit late, so let me just state the last thing that we have to go on. Is there another? Yeah, just state the last thing, and then, so we have two equations here. We have a third equation, which I'll shortcut this little derivation and just say that, remember, we know, how do I say this now? We know that, if you trace back where this came from, it came from varying lambda at the endpoints in the action principle. We know that when you do that, p squared plus m squared equals, we had this equation before, right? It tells us that in the massless case, it tells us that p is a null vector, and in the massive case, it tells it's on the mass shell, as one says. I was going to repeat the derivation, but I won't bother. And so that's our third equation, which is that p squared plus m squared equals 0, or p squared equals minus m squared. And remember, of course, p, as always, meant dx d lambda along the geodesic. And so let's just see what these equations are. So this was minus p naught. Now what is p naught? P naught is the covariant component. So since there are no off-diagonal components to the metric in this choice of coordinates, it's just minus g00 times the contravariant component, which is minus, what was it? Which is plus h squared, I guess, was g00, and p0 was dx0 d lambda, or in other words, dt d lambda. So if we call x0 t for convenience. So this thing is conserved. This is one of our conserved quantities. And in the same way, if we work out what, so now we'll see. Now you'll see where the r is coming in. So by the same calculation, if we want to relate this to the tangent vector, we have to have g phi phi times p phi. But what is g phi phi? That's g phi phi times d phi d lambda, right? P phi is d phi d lambda, that contravariant one, just because of this equation here. And g phi phi, now you look up at the g phi phi, well, here you see sort of sine squared theta d phi squared, but we're at theta equals pi over 2. So it's just r squared d phi squared. So g phi phi is just r squared. So it's r squared d phi d lambda. And then our third equation is this, which says, I won't bother to write it out now, but you can just plug in, you just have to substitute in GAB dx A dx B over d lambda twice equals minus m squared. Okay, so now we see, so we have these three. You can actually think of this, if you like, as a kind of conservation law associated to the lambda invariance, but for whatever. But anyway, we have these three equations, and we have, in our orbit, we have really, now let's just count variables in equations. So we have, to describe the orbit fully, we need, that is the trajectory, the space-time world line, we need to talk about the time. We talk about the radius, we need to talk about the angle. We've acquired theta we don't need because we've arranged it to be pi over 2. It's in the xy plane. And we also need lambda, because lambda is our affine parameter. So we have 4 variables, and we have here 3 conservation laws. So we can use 2 of them to eliminate 2 of the variables. And I guess, what will I eliminate? I'm going to eliminate lambda, I guess. Yeah. I'm going to eliminate lambda and t. So we'll be left with just the equation in r and phi, which will define the orbit of this particle. And so we'll be left, that'll get it. I'll use 2 of the conservation laws to eliminate t and lambda, and then we'll be left with 1 equation for r and phi and 1 conservation law. So that's a very familiar kind of situation. And then it'll be essentially, if you treat phi as the independent variable and r as the dependent variable, then you'll just be left with something that looks like a mechanical problem. It'll just look like a particle moving in an effective potential, and we'll solve it that way. And that's where we'll start next time.